We start first by types of fluid. Actually, we classify the flow in different categories according to the type of classification. And there is no, we can say there is no interaction or relation or confusion between one and the other. Each one is a separate classification for the flow itself. So when you're going to classify a flow, it should be classified as first one like steady and unsteady, and also we can classify as a laminar and turbulent, and also we can classify uniform and then non-uniform, and so on, compressible, incompressible, and so on, the others. Once I said to you the fluid is steady, it does not mean laminar direct or non-uniform or rotational. No, each one have a parameter, should be studied this parameter to know this flow according to this parameter related for this classification. It is this one or this one. Clear? The big confusion for this classification mainly between two, which is two, steady and unsteady, and uniform and non-uniform. Many engineers make a big confusion for these two. This flow, it is what? Uniform, non-uniform, steady or unsteady, or whatever. He said to you, according to this information I have, this is steady. But actually the information is referred to the uniform or non-uniform, not related totally for steady or unsteady. So we need to first to define how to know this flow is steady or unsteady, or this flow is uniform or non-uniform. You remember the velocity definition by last session? Velocity definition by easy definition, the rate of a change of this distance or displacement. So it is a function for displacement with time. Correct? Yes. So the mainly two parameter control for the velocity, one is displacement and one is time. One is displacement and one is time. To study the flow, steady or unsteady or uniform and non-uniform, we're going to study this velocity one time with displacement at constant time, and another study with time at constant displacement. So what I mean, we study the velocity in two ways. Way with a change of x at t equal constant, and the other way which with t at at x equal constant. We need to more information to understand for that. To be aware, here x, so we study this one with this one. It means by default partial v partial x, the change of velocity with displacement. Here with t, which is mean partial v partial t, we study the velocity with time. Okay. Okay, what's meaning also? We need more to be understand. If the flow, I study the flow, for example, inside a pipe. Okay. If you study at a certain position x, so at this time x equal constant. Correct? Because I study what? The flow at this position. I study the flow at this position. So in this case, we study at x equal constant. It means you study the velocity with time. It means I just check the velocity here with time. What is the velocity with time? In this case, if the velocity with time at a certain position not a change with time, it means this one is steady. Is the velocity it changed with time at a certain position, so this one is unsteady. So classification for steady and unsteady, this related direct to study the velocity with time at a certain position. But if you need to going to study uniform and non-uniform, means I study time, constant time at different position or with displacement. So what I mean, at the same pipe, but at a certain time, I study the velocity at different displacement at x equal 1, at x equal 2, at x equal 3, at x equal x, at x equal whatever. So I study different displacement, but at certain time. If the velocity at this different position not a change, so this one is uniform flow. If the velocity profile it changed with this different position, different locations, so this one is a non-uniform. So non-uniform and uniform, it means study the flow with displacement at constant time. So this part is classified uniform and non-uniform. But this part is classified the flow is steady or unsteady. Clear or not?
Clear.
Yes. Yes.
Normally, the question is coming by figure or whatever, by written or anything. It can written or it can by figure. You can describe the flow is uniform or non-uniform normally. Okay, but steady or unsteady, it's difficult to just I see the figure and I know the flow is steady or unsteady. It's difficult. It should be give some information to know this flow is steady or unsteady. But one case we can know this flow is steady or unsteady, and I will tell you which is this case we will see, but after some time. Okay. Okay. Second classification, third classification now, laminar and turbulent. Okay. Now we finished two classifications: steady and unsteady, uniform and non-uniform. So I can say the flow is steady, uniform, or steady, non-uniform, unsteady, uniform, unsteady, non-uniform. No problem. Okay, this classification with parameter, this another classification with another parameter. Okay, laminar and turbulent. Laminar and turbulent. Laminar and turbulent, if the flow is going as a one set in straight line, this laminar or turbulent.
Laminar.
Okay. But if the flow is going as a one set also, but in zigzag.
Turbulent.
Or turbulent.
Turbulence flow, that one.
Is laminar too. But if the flow, it is not going together, not a coherent layers moving. So we have some eddies, some vortex rotations or circulations for the flow anywhere. So this one is turbulent flow. Okay. 1, 2, 3 dimensional flow, one dimension, straight line, 2 dimension in 2 directions. Flow is moving in one direction and another direction also change. 3 dimension, it means the flow it changes in 3 directions. Compressible and incompressible. Compressible is direct relation between pressure and volume. You remember bulk modulus of elasticity, which is easier to press and something like this. But yes. Here, no, we need not easier to press or not easier to press, just we need to, it can press or not. Okay. If the pressure apply, make a change in the volume, so this compressible. If don't make any change in the volume, this incompressible. So if the pressure apply here, P1 is bigger than P2, P1 is not equal than P2, or the case of P1 and P2, we'll see the figure is better. I will see the figure is better to describe clearly. Rotational and irrotational flow, just this mainly for the particle itself, particle for the flow. If the particle itself is rotated along on its axis, it's rotated along on axis during the flow is moving. Whatever the moving is straight, just have a movement flow totally. But we focus for particle. This particle is rotated along on axis or not. If rotated along on axis, this rotational flow. If not, this irrotational flow. We'll see also the slide for that. Let's see. Here is steady and unsteady. So it's discussed already. Uniform, non-uniform. This one of the special case. You can imagine the flow is steady or unsteady direct without giving information or extra information to be aware this is steady or unsteady. From where? Especially for this case, like this cylinder or tank. This tank have at the end orifice here. When you're going to study continuity and Bernoulli, what we will study today, inshallah, we will see to calculate the velocity here, I need to know the velocity here at the exit of the orifice here. To know the velocity at this exit, the velocity after apply the equation for continuity and Bernoulli, you will find the equation for velocity is equal to root 2gh. I think many engineers see before these equations, correct? So which h? H is the height of the tank. So the velocity is directly proportional to what?
Yeah.
The h.
Yeah,
And according to Qn and Q out, I don't know Qn equal Q out, or Qn is more than Q out, or Q out is equal to more than Qn, whatever. So the h is vary, correct? If the h vary, it means the velocity the same varies also. So the velocity crossing this cross section, it means at a certain position, constant or vary.
it increase.
Increase or decrease according to the h level, correct?
Yeah, it will vary.
So
varied, yes.
it means it what? For sure, it is unstable,
Yeah. Okay.
correct?
Correct.
But I need to going to the second classification, uniform or non-uniform. So this depends on the pipe, the shape. Check the pipe. If the pipe uniform like this, so if I check the different position, normally the diameter not change, so the velocity not change. Why? Because we see the continuity equation relation between velocity and the diameters or area. So diameter not change, velocity not change. But in the case for the pipe, something like this, or the pipe orifice like this, for example. If like this, so the position here not the same there, not here, not there, and so on. So different change here for the velocity with positions. So in this case is non-uniform, but in this case is uniform. In this case, change in diameter, non-uniform. Clear? So from the figure direct, we can imagine and know the flow is uniform or non-uniform. In the special field like this, we can imagine also understand the flow is unsteady flow. Clear? A flow through an expanding tube at constant rate Classify the
B.
flow.
B.
Flow.
Constant rate, steady.
um,
Expanding tube, non-uniform flow. Expanding tube,
Yes. Steady non-uniform flow.
non-uniform. Steady because he mentioned here constant.
Yes. Yes. B.
Okay. Yes.
Laminar and turbulent, actually also we discussed this one. This
Yes.
laminar, whatever is exact straight, but adjacent to fluid layers move mostly with respect to each other. Coherent layers. Okay, but turbulence, it is motion of different sizes and intense cross-stream mixing. Viscous and inviscid flow. Viscous and inviscid flow. You remember viscosity? Viscosity, it is effect on the flow. Viscosity, layers have a velocity gradient between layers, so the velocity is not the same along the locations of the flow. For example, as you see here for the first one, this pipe, tube, so it is constant from the pipe itself, surface of the pipe, and the maximum from the center. Why? Because this highly viscous flow. Highly viscous flow. So viscous flow, it means the effect of viscosity, it is dominant for the flow. It is effect on the flow. Actually, almost all properties in the fluid happen, but normally one is dominant, other it is small. So we mean what happened for this case? I see this happen by surface tension. No, it still happened by viscosity. No, it is happened by pressure. No, it is happened. So actually, it is all happened. But one of this, for this case, is a dominant. So this, it is created by viscosity. This created by surface tension. This created, the effect here is bigger by pressure. So you understand me? According to what is the main or big effect. Here, viscous flow, viscosity creates shear stress that affect on the dynamic of the flow. Okay, as you see here, whatever flow is laminar or turbulent, no problem. But in viscid flow, the force due to viscous shear small, same like the second shape here. You see, almost a flat profile. Almost what? Flat profile. It's just here a small change, and here a small change because this is close from the surface, so it's almost still close to zero. When you're going to make zoom for this part, we'll see something like this. And we can mention for this part is a boundary layer. For the boundary layer, it is close to the surface, so the effect of viscosity it is high. But when going in the middle, we will see inviscid flow. Totally, we can describe this flow as an inviscid. But if the effect like this is bigger, so this flow is viscous flow. Clear?
Again,
Questions?
inviscid flow.
Again?
Again, one time explain, sir.
I didn't hear you.
Yeah. Viscosity, okay, I understand. Inviscid flow, that one is not understand. Again, one time.
Viscosity is okay for you, no problem. But what is not okay?
Second one. Inviscid flow. Yeah, second point.
Second point, inviscid flow. Inviscid flow, the effect of viscosity and create shear, it is very small in the flow. The value of the fluid have a viscosity. This is a property for any fluid, but this is small, not big. So the effect for viscosity during the moving of the or dynamic motion of the flow, it is small. So the flow is going as a flat profile. No, don't have a velocity gradient with which is coming from the shear stress effect.
Okay.
Okay. What is added here, at least still, what is contact in the surface is still affected by the surface itself, because at the surface, at least you have a big fraction.
Yeah, okay.
Okay, but overall, not effect. So is it? We can say inviscid flow.
Okay.
Compressible and incompressible, this already also described here. As you see here, B2 is larger than B1, but the volume is not a change. So this one is incompressible flow. But here, B2 is larger than B1. What happened for the volume? Is decreased. So we have a proportionality. It is inversely proportional between pressure and volume is happening here. So this compressible flow. Normally compressible flow like gases, normally incompressible fluid like liquids. Volumetric change of the fluid caused by resistance is known as
Compression.
Compression. C.
volumetric change is related directly to
Compressibility. C.
compressibility is correct. The answer on chat is C. Yes, correct. Compressible. Here, last one, rotational and irrotational flow. The flow is moving like this, okay? During the moving the flow, whatever the moving is the straight, whatever this moving of the fluid is rotation. No, it is not related to describe the flow is rotational flow or not. How can I describe that? When you study the particle itself, how can I describe this particle? Check particle. If the particle is not rotated along one axis, so same like the first one, upper one, so this is irrotational flow. But if it is rotated along one axis, this is rotational flow. Clear?
Yeah, yes.
Okay, this is clear or need video to understand further?
Sir, then what is the what is the distance? What is the difference between rotational flow and laminar flow then?
No, rotational and turbulence. I also want to ask.
Yeah.
Actually, classify the flow separate. Don't mix between others. Study each one by each parameter related for that. Okay? Maybe the rotational flow is rotated, but rotated coherent. Okay? I know it is so slightly difficult or slightly.
Irrotational and turbulence also flow is changes, correct?
What?
Irrotational and turbulent flow, that one is also same flow, correct?
Irrotational and rotational, it depends on the particle itself. See with me. Just wait. Wait.
This is a flow pattern can be approximated graphically or mathematically by the with the radius. Obviously, lines are fixed either tangential or normal to the stream.
All see screen?
Rotate, just
Yes.
as they would the vortex seen before. However, if the velocity varies inversely with it, as it tends to do in the field of flow surrounding the vortex filament, whether above a drain or in a tornado, a line or stick in the tangential direction will tend to rotate in the opposite sense from one of the normal, but at the same rate.
Light off will work.
Two perpendicular sticks fastened together will then not rotate at all. Such flow is called irrotational. The central filament itself, of course, is highly rotating. Flow in concentric circles is not the only kind that is sometimes highly rotational and sometimes almost irrotational.
This is
Uniform
flow,
between
rotational
parallel
flow.
walls is usually rotational.
This is the particle is rotated along one axis.
either non-uniform or unsteady flow that is rapidly accelerated is very nearly irrotational.
This irrotational.
Now, the
Even
important
if it
part
is
about
also
irrotational flow
have
is
some
that
turbulence here at
can
this
be
connection,
approximated
but still
graphically
irrotational
or
flow.
mathematically
Okay,
by the construction of a network of streamlines and normal
enough,
lines, which are
enough,
Okay, sir.
enough session, enough video.
Everyone confused.
So irrotational flow, sir. What will be the action of agitator? Like agitator used to rotate. That is a rotational flow, right?
Irrotational flow when the particles is not rotated along one axis during the movement of the flow, whatever the flow is totally movement or not, or straight or whatever, but
Like
the
if
particle itself is not rotated.
like if the agitator is moving in this direction and the particle is also moving in that direction, so that will be a rotational flow, right?
If the particles, yes, is rotated along one axis.
Okay. And if the if the direction of a particle is opposite the direction of that flow, sorry, the rotation, that will be irrotational flow.
Opposite?
Yeah, opposite side.
Why? You can take it as a clear. If the particle, check particle itself. If the particle
Okay.
during the moving move with the flow without any rotation, so is irrotational flow.
Okay.
If the particle during moving the flow and also this particle itself movement rotated during movement, so this rotational flow.
Okay. Now I understand.
Okay.
Now it's clear. Okay.
I have the question. Is it the turbulence and rotational flow exist at the same time?
Turbulent and irrotational, or turbulent and rotational?
Turbulence and rotational
I think both can be happening.
together.
Turbulent with rotational and turbulent without with irrotational.
I see.
Because same like steady and uniform, steady and non-uniform. This all totally is different descriptions. Okay.
Yes.
Studies the flow separate.
So flow can be rotational flow also, but in a laminar
Yes.
path. Yes.
Later of water occupies a volume of 1000 centimeter cube.
Answer?
1000 centimeter.
Occupies a volume of 1 liter.
Answer?
1 liter.
1000 centimeter cube. 1000 centimeter cube.
1 liter. 1000
Divided by 3.
1000 centimeter cube. Yes. One dimension flow.
dimension for the flow is steady and uniform, takes place in the straight line, takes place in one direction.
Straight line. Straight line. The fluid is said to be ideal when
Incompressible. A.
only incompressible.
Yes. E.
In viscous and incompressible.
Incompressible.
Let's start for one of the famous equations.
Sir, any example of ideal fluid? Water?
Ideal fluid. Just wait, I can check. I don't remember now, but I can check.
Because water is incompressible, but I don't know whether it is viscous. Yeah, maybe it is a viscous.
I check also. Ideal fluid. Ideal fluid, ideal fluid. Ideal fluid examples. Yes. Yes, like water.
Okay.
Is fluid in fluid? Yes, like water. Yes.
Okay, sir.
Okay. Just a minute. Okay. Continuity equation. I think, oh, I didn't see exam without continuity equation. Very important in the exam actually. Okay. First equation for this one here, this is general one, just I described to you quickly. But actually we will focus for the small part. Okay. This is which is coming in the exam. General equation of continuity. What before we start for the equation, what's the definition for continuity equation? Continuity equation is conservation of mass. Conservation of mass. What he mentioned here, d by dt mass by control volume is a plus sum of m dot out minus sum of m dot n is equal to 0. The change of mass during the control volume, which is the part of study, okay, plus the masses out minus masses in is equal to 0. Mass out is clear. This is the all masses out from the control surface here. For example, this pipe is clear. We have out, we have in, this clear. If I draw like this here, this tank, we have one like this, one like this, one like this, and this is the control volume for study. So I mentioned for this in, I mentioned for this out, I mentioned for this out. So here in this one, we have some of input for the flow. We have some of output, whatever this one in or more, like this to output. So this is the sum of m dot out, sum of m dot n. Okay. But this one, d by dt m control volume, This is the change of the flow inside this one. You remember the case of unsteady uniform and the tank for that? This is
Okay.
same like this. This describes the change of the masses inside. Whatever is increase or decrease, this measures that. Give a relation to measure that. Okay. Normally,
So
the
that is
questions coming in the exam is a special case for this. What's the meaning of special case? Special case from this case, normally we asking for pipeline. And for any pipeline, if you put something like this pipeline, whatever this pipeline is regular shape or not regular like this, whatever pipeline have a clear inputs, whatever this one input or more, and also have a clear output. So we don't have anything inside. Anything going to the pipe shall be going from outside. Whatever pipe, this network like this, have something like this, flow coming like here and go out from this way and this way. So we have one input to output, flow coming like this, and so on. This input to input, one output to output, and so on, whatever. But at the end, this pipeline. So anything going in shall be going out. So in this case, we don't have any study for the area of the control volume inside. No study for this area totally. So in this case, this one is 0. And the remaining is what? Sum of m dot out minus sum of m dot n is equal to 0. But this other side, we will find the final equation for that. Sum of m dot n equals sum of m dot out. Or we can mention m dot n here, same like this case, m dot 2 equal m dot 1. Clear? This is the continuity equation. Very important equation. So we use it in the exam a lot. M dot n equal m dot out. What is m dot? Mass flow rate. Mass flow rate. And then it's for this 1 kilogram per second or bound mass per second. Or we have another different units for bridge slug per second. I don't remember. Maybe we have one more for bridge also. Okay. What is m dot? Actually, m dot is equal rho times A times V. Rho times A times V. Okay.
rho times A into V, density, area,
Rho
and velocity.
Times A times V. What is rho? Is density. A is area. V is velocity.
Velocity.
V is velocity. Okay.
Okay.
And in a special case for these cases, which is incompressible flow, in incompressible flow, the density not a change. For compressible density change, according to the relation between pressure and volume, we have a change in density. But for incompressible flow, normally for water, oil, and something, density not a change. So we can cancel density from both sides. And in this case, we will find AV equal AV, which represent is Q. Which represent what? Q. And what is Q? Volume flow rate. It's more famous and more used in the exam, more than m dot. Sometimes we use m dot, but normally we use m dot in case the flow is gas, which is have a density change. But normally for incompressible flow, we use it this way. Qn equal Q out, which is AV equal AV. I can represent it like this. You know the happy face? Okay, don't forget this for the exam. Q is equal what? AV. Okay?
AV.
Yes.
Okay, so the top one is the compressible fluid, below one is incompressible fluid.
Yes, it depends on the density. Density effect is in the equation or not.
So density for incompressible density for incompressible liquid is 1, right?
Not 1, but it is constant.
Constant, okay.
Q dot here have a different and a lot of units. For SI unit is easy, just meter cube per second. but it's for British a lot. Feet cube per second, CFM, feet cube per minute, GBM, gallon per minute, LBS, liter per second. A lot of units for cube. Be careful for cube, please. Any question? Any question?
No.
No, thanks.
Ideal flow of any fluid must fulfill the following.
Ideal must fulfill the following.
Ideal flow of any must fulfill the following. Equation.
Which
Ideal
one?
flow must fulfill D. D.
Continuity equation. Correct.
Ideal flow.
Let's see the other important equation. Bernoulli equation. Bernoulli and the continuity is double. Okay. Normally the problem is coming for continuity, we be coming to cover continuity only. But if the equation or the problem coming to cover Bernoulli, normally we need to use it in continuity in the steps, during the steps for solving. Okay. Major is continuity, this one. Bernoulli equation. What is Bernoulli equation? Actually, Bernoulli equation is one of the equations to describe the energy in ideal case. Energy, it means energy equation in ideal case. Energy without losses, okay? Without including losses for the equation. So next session, inshallah, we will see this equation again, but including losses, which is clear energy equation, okay? But here, just Bernoulli equation, energy equation along streamline. Okay. Important? Yes, important. I will give you one problem direct from the exam with numbers. It's coming a lot, related and solved by Bernoulli and continuity. Okay. Some of this total energy along the streamline is constant. So the total energy is equal or constant. Total energy is constant. This total energy is divided in 3 types of energies. But at the end, the total is constant, whatever at any point along the streamline you study. What is this energies? Flow energy, potential energy, kinetic energy. Flow energy, which is including pressure, potential energy, which defines the altitude or effect of altitude, elevation, and the kinetic energy, which is including the effect of velocity. This in the form of energy. Back to the first session or the last session. You remember I tell you the pressure we can describe as a pressure form or head form, correct? Same like bumps. Because the pressure is equal gamma H. So I can describe the flow, pressure of the flow by pressure direct, or I can describe it by H, the pressure for this one, head of this one, blah, blah. Head of this one, it means refer to pressure effect. Here also, we can write the equation in the energy form, or we can write it in the head form, or we can write it in the pressure form. Actually, the lowest one for usage, energy form. The highly one for usage for the equations and solving and some studies, head form. Medium one, pressure form. Okay, this is the grade for each one. The highly important one, head form. Okay, which one is head form? This one I mentioned here for head form. Pressure form is not here, but I can write it to you on the board. Okay, head form, it means the unit for each term like this, between 1 and 1. The unit for each one should be unit of head, unit of length, correct? So to describe that, we need, this one is described for H. So should be divided by gamma to describe H. To be divided by gamma, we need to multiply, divide all this equation by G. Here, B by G rho, which is B over gamma, which is referred to the unit of head. This divided by G, it is cancel G and the remaining Z. This divided by G, which is 1 over V square over 2G, V square over 2G. So the final equation is B over gamma plus Z plus V square over 2G equal constant. Don't forget this equation, please. Seem like happy face. B over gamma plus Z, both it refers to piezometric head. You remember piezometric device? This piezometric head. B over gamma plus Z, it refers to piezometric head. And the other one is velocity head, not kinetic energy, because this one is head now, refer to the head. So this mentioned to velocity head. Velocity what? Velocity head. So sum of piezometric and the velocity heads along the streamline is also constant, same like the energy. The total energy is constant. Also, the total heads is constant, piezometric head and the velocity head. Okay, so this means that the pressure decrease as a velocity increase. Pressure decrease, velocity increase to keep the total energy constant along the streamline and vice versa. Whatever is also velocity decrease, pressure increase to keep everything the same for the total energy. Last thing here I want to mention here, piezometric head I can mention to a static head. A static. Velocity head is can mention here dynamic head. So static head plus dynamic head is equal total head. Total head. Again, the part for piezometric head is referred to static part. So this referred to static head. The part for velocity head is referred to dynamic part. So this one is velocity head or H dynamic. Okay, and this total energies, total heads is equal to constant, which is referred to total head. Okay, I tell you, I will describe last one for the pressure form. B over gamma plus Z plus V square over 2G equal constant. Correct? This what? Head form. I need to obtain pressure form from this one. To obtain pressure form, it means the unit for each term is pressure. So we need to cancel gamma from this one to obtain pressure alone. So if you need to cancel gamma from here, should be cancelled from all. To cancel gamma, we need to multiply gamma for each term. Gamma multiply B divided by gamma, which is B, plus gamma Z,
Gamma Z
plus here gamma is actually rho G. So G cancel with G. So it's rho V square over 2 equal constant. So this is the last form with it referred to pressure form. This is still piezometric, but here piezometric pressure. Piezometric pressure. Okay, and this one refers for velocity, but it's difficult to mention velocity pressure. We can mention direct dynamic pressure. Dynamic what? Pressure. So this piezometric pressure or B static or B piezometric plus B dynamic equal B what? B total. Same like this, equivalent for this. H static plus H dynamic equal H total.
Oh,
normally we use this one a lot, this one sometimes. Okay.
Okay. One is pressure head, one is pressure Bernoulli, and one is the head.
All is Bernoulli's, but different shape. Okay.
Sorry, doctor. I lost. What is that?
Z is elevation.
Elevation. H.
Yes, like by like this. So this elevation 1, this elevation 2. If you study, change what happened between this along the streamline for this distance. This elevation 1, this elevation 2.
Understood.
Here, just I put the charger Just 1 minute. Any question? Back to the slide. Okay. Read carefully and answer, please. And it's very important question. Okay.
D.
Hello.
Yes.
Oh.
B.
D.
A.
No, it's D. Correct. All of them.
D.
Yes. D. D for draft. Euler's equation. Euler's equation is similar like Bernoulli equation, but different approaches. But just I mentioned here for the definition for Euler, I don't present here for the equation itself. Equation is not easy. Also, it's coming in the exam. It's not easy. Solve the same type of problems, but not slightly. It's higher version for difficulty from motion and the effect of the acceleration and something like this. So used to study pressure variations. And Newton's law of motion applied for the fluid particles for inviscid and incompressible. For this equation, applied for inviscid and incompressible. Just a small information like static pressure. It is a pressure of flowing fluid at any point. This is static pressure. Same like barometric pressure, we study a point, and this is according to the raising in the pipe. This refers to static pressure. Pressure tab, it is a small hole in the pipe. Read carefully this problem. This problem is similar to the problem in the exam. Similar figure, similar number. Take 1 minute for reading, understanding, check figures. Finish reading. Reading finished. Okay, first thing, I ask you one question. We have two pipes, correct? Why the height inside these two pipes is different? And don't tell me one is I shape, one is L shape.
Because of the area of the pipe?
Location of the point?
No, both measure the same point. Consider
diameter of the pipe or something?
Because this is like
smaller diameter.
Small? No.
Different velocity.
What is the velocity for each one? You are close, but give me more.
It's invicted floor.
Again? With me?
Is it because velocity is proportional to the head?
Both is measure the same point here. This refer to this point. This refer to this point. We can mention like this. This one is measure this point. This one is measure this point. Any idea? Focus with me. Very important, please. Steps at the end, we found 3-4 steps and finish. But be aware for the idea. The flow is moving, correct?
Yes.
So here, still moving. So this pipe is measure what? Piezometric, correct? Correct or not?
Correct.
Piezometric, same like piezometric device. Piezometric device like this.
Yeah,
So
height is measuring the height.
Device here refer to the point measure, correct? Piezometric device, pipe are above this duct, so piezometric. So B static or H static, which is head actually, correct?
Yes.
But here, the flow is stagnant. I mentioned here, stagnated at the head of a very fine pure tube as shown in the figure flow. And the water is 12 inch. So for that pipe raises 12 inch, the flow is stagnant. Stagnant, it means velocity equals 0. So at this point, no velocity. Bernoulli equation. Conservation of energy. Conservation of energy. Where does this energy go? Where does this kinetic energy go? Where does this part of dynamic go? It's converted to
pressure.
pressure.